We are going to look at section 12.4, which is binomial probability. We've seen probability distributions in one of the previous sections, but we're just going to remind ourselves what a probability distribution is. It is a description that gives the probability for each possible value that a random variable can have. And to be a probability distribution, the sum of all of the probabilities must be 1, and all of our probability values have to be between 0 and 1 inclusive. So they can be equal to 0, they can be equal to 1, or somewhere in between. So an example is a table, but charts are also forms of probability distributions. So we've just looked at general probability distributions. And today we're going to look at a more specific one. We are going to look specifically at a binomial probability distribution. So a binomial probability distribution is going to be a probability distribution that has to fulfill the binomial settings. And there are 4 settings. We use the acronym BINS to help us remember them. So the first is binary. The trial must have 2 possible outcomes. So for example, when you flip a coin, heads or tails, that has 2 possible outcomes. Another example, drawing a card from a deck. Probability of drawing a queen. That has 2 outcomes. The card that we draw is either a queen or it is not a queen. The trials need to be independent. So therefore, if you're talking about a deck of cards, we have to be dealing with replacement. We cannot be taking a card out. The outcome of a further item happening, such as when you draw cards, cannot be dependent on something that has already taken place. Then N stands for number. The procedure has to have a fixed number of trials. And our S stands for successes. The probability of success has to remain the same in all of our trials. So we're going to look at some examples to help us understand this a little bit better. Our first example, it says, imagine a fair 4-sided die with the numbers 1 through 4 on each side. Construct a probability distribution where X is the number of times that a 3 is rolled in 2 rolls. So we're looking at the number of times a 3 is rolled in 2 rolls. Our tree diagram is going to help us. So when we start off, we have the option of getting a 1, a 2, a 3, or a 4 on that first roll. And then our second roll can be a 1, 2, 3, or 4. So if we wanted to write out our entire sample space, we could get a 1 and then a 1, or a 1 and then a 2, a 1 and then a 3, a 1 and then a 4, a 2 and then a 1, a 2 and then a 2, a 2 and then a 3, a 2 and then a 4, 3 and a 1, 3 and a 2, 3 and a 3, 3 and a 4, or 4 and a 1, 4 and a 2, 4 and a 3, 4 and a 4. This is our sample space, and our sample space is going to help us to create our probability distribution. Our probability distribution is going to be a table where X is the number of 3s that are rolled, and our other column is going to be the probability of X happening. So how many 3s can we roll? Well, we have the probability. So if we roll a 1 and then a 1, there are 0 3s that have been rolled. If we roll a 1 and then a 2, 0 3s have been rolled. If we roll a 1 and a 3, 1 3 is rolled. And the only other thing that we could have happen is we could have 2 3s being rolled. To find the probability of each of these happening, we have to count up how many times it occurs. So no 3s were rolled. Well, this one, so 1 and 1, there is that one. This one has no 3s. 1 and 4, 2 and 1, 2 and 2, 2 and 4, 4 and 1, 4 and 2, and 4 and 4. Each of those has no 3s that have been rolled, and there happens to be 9 of them. So 9 out of our total of 16, and that happens to be 0.5625. Then we look at how many 1s could we possibly roll, or excuse me, how many times could we get 1 3? Well, a 1 and a 3 gives us 1 3. A 2 and a 3 gives us a 3. A 3 and a 1, a 3 and a 2, a 3 and a 4, and a 4 and a 3. Those are all the ways that we could get 1 3. And there are 1, 2, 3, 4, 6 of them. Or 0.375. And there is only one way in which when we roll our die, we can get 2 3s. So that's 1 out of 16 or 0.0625. So that's the process of constructing a probability distribution. Now, we've seen that oftentimes we have sample spaces that are much larger than just 16. And so we need a way to be able to create a probability distribution without having to write out the entire sample space. And that's where the binomial probability distribution is going to come in handy, because there's a formula that we can use to help us do this. So let's first look at some things to determine if they are binomial distributions first. So example 2 asks us to determine whether the random variable have a binomial distribution. So really what this is asking is, does it fulfill bins? If it fulfills bins, then we know that we have a binomial probability distribution. So we have to look at each of those. So B, we said that B was binary. There has to be 2 possible outcomes. Here we are rolling a fair die 10 times, and X is the number of 6s that are rolled. Well, we are going to have 2 outcomes. It's either going to be a 6 or it's not going to be a 6. Now, really it's going to be numbers 1 through 6, but because X is the number of 6s that are rolled, we don't care if it's a 1, 2, 3, 4, or a 5, because those are all not 6s. So therefore, we have 2 outcomes in this case. So that one has been checked off. It fulfills it. I, independents. Are the trials independent of each other? Well, when we roll the die and then we roll it again, those 2 outcomes are going to be independent of each other. What you roll on the first die has no bearing on what's going to happen the second time the dice is rolled. So our outcomes are independent. For N, we need to have a fixed number of trials. Well, it tells us that we are going to roll the dice 10 times. 10 is a fixed number. And then our S says that the probability of success has to remain the same all the time. So in this case, our probability of X, or our probability of rolling a 6, is going to be 1/6 for all trials. And so that successes has been fulfilled. So therefore we can say that this is a binomial distribution. So therefore we can say this is a binomial distribution. Part B. Shoot a basketball 20 times from various distances on the court. Let Y equal the number of shots that are made. So first we need to know if this is binomial. Are there two possible outcomes? Well, there's going to be two possible outcomes. You're either going to make a basket or you're going to miss. Independent. Are the outcomes independent? They are. If you make the first shot that you take, that doesn't necessarily tell us that you are going to make the one right after it or miss it. For N, does it have a fixed number of trials? They told us that it's going to be 20 shots. So therefore, 20 shots is a fixed number. So we've met B, I, and N. Now we need to look at S. The probability of success. Well, it told us that we are taking shots from various distances. Since the distance is changing, that's going to change the probability that we make the shot. If we're really close to the basket, we're easily going to make the shot. But if we are far away from the basket, the probability that we will make that shot is a lot less. So in this case, the probability of Y is not always the same, since we are changing distances. That one is not fulfilled. The S is not fulfilled, therefore this is not a binomial distribution. And for C, it says, observe the next 100 cars that go by and let C equal the color of the car. B, binary. Are there two options? Well, the thing that we are observing is color, and we have more than two colors. So automatically, this cannot be binomial. So not a binomial distribution.